Hello. Today we'll be talking about the volume of pyramids and cones. Before I give you the formula for pyramids and cones, they're very similar, we're going to perform kind of like an experiment on paper. It's easy to derive the formulas for these things with calculus, but of course we're not there yet. But we can borrow a technique and see what happens. For instance, suppose we have this pyramid here. Now let's look at it straight on from the side. What would we see? Well, we just see this triangle here, right? That's about all you'd see if you look at it just dead on from the side. And suppose we break this pyramid up into, let's say this is 5 feet. Just attach a unit to it. If the altitude is 5 feet, and we'll say this side here is 5.8 feet. We can create or stack a bunch of boxes, which we now know would be called rectangular, or in this case, square prisms. We have a square pyramid here. I probably should have mentioned that. This is a square here. So we can consider this a square prism, or what some people would just call a kind of flat box. It's 1 inch high and has a square for a top and a bottom. Pretty simple. So what would the volume of this thing be? Well, it'd be the area of the square times this height, which is just 1 inch. So just 5.8 squared. That'll be 5.8 this way, and then 5.8 that way. Times 1, which is just 5.8 squared. Same thing here, 4.6 squared, 3.46 squared, and on up. So the area of all these little prisms stacked up, which of course gets successively smaller, is equal to this. Where in the world would I come up with these other numbers? Well, this is 5. This is 1 foot, so this is 4. Remember, a tangent is opposite over adjacent. Well, the adjacent, now these are equilateral triangles. So this is 60 degrees, and this half of it here is 30 degrees. That matters because we can consider this to be perpendicular. We can just draw a line here parallel to the side in order to figure out how long the side is, because they will be congruent. So the tangent of 30 degrees would be opposite, that's x, which we haven't found yet, over 4. Well, that implies that x equals 4 times, and tangent of 30 is 1 over the square root of 3. And we get 2.3, but that's this half right here. We have to double that to get the whole length from here to here. And of course multiply that by 2 and get 4.6. And we just keep doing that, and I get 3.46 for this length, and on up. You can go ahead and check that if you want. I'm pretty sure my calculator did it right. We add all these up, and what do we get? 73.38. So what? This is obviously more. These edges extend out beyond the boundaries here, and if you look at it from the three-dimensional point of view, you can see that our square prism would be larger. It would stick out from this thing. Suppose we used what you could call in some math courses, doing it this way. As we get these things smaller and smaller, suppose they were a 1/2 inch, and then a 1/4 inch, and then an 1/8 inch. When we added them all up, they would get closer and closer to the actual volume here, but they would always be larger. So as we keep doing these outer boxes or prisms, which from the side view just looks like rectangles, we get closer and closer to the actual volume, and that means that we can call this an upper bound. It'll always be larger, but it could get really, really close. Let's leave it the way it is for now. Let's consider another way of looking at this, breaking it up into square prisms. Let's do it this way. Let's produce some more square prisms, but make sure that they never extend beyond the boundary, which means that we've left out this little bit of volume every time. Or if we look at it over here, this pyramid would always extend beyond our rectangular prisms. So these are always smaller. Now we could cut down the height of these things, and we get more and more and more of them. As we got more, the volume of these yellow prisms would increase and get closer and closer to the actual volume of the pyramid. In mathematics, we call this a lower bound. So the yellow ones form the lower bound, and the blue ones form the upper bound. Now, once before we tried something like taking two numbers, one was too big and one was too small, and we took the average, and it worked out pretty good. We did that with trapezoids, where the lower base was too big, the upper base was too small, but if we took the average and pretended that that was just the base, and then multiplied that by the height, we wound up with the area of the trapezoid. Can we do something like that with this? Let's see. Well, if I add all these up, I've really got just about the same thing, except that I don't have a 5.8 in here anymore, because this from here to here is now 4.6. It has the same length as the upper blue one, or the smaller blue one. This one now has length 4.6. This one has length 3.46 on up to 1.15. So it's 4.6 squared plus 3.46 squared on up like that. That turns out to be 39.74 if you want to add up all those squares. Now what we're going to do is take the area we got from the blue prisms plus the area we got from the yellow prisms, take the average, and see what that gives us. So if we take the area of all the yellow prisms, add them up, we get 39.74. Now let's take the average of these two. One's too big, one's too small. An average is 56.76. If we multiply that by 3, that's 169.7. In other words, 56.76 is 1/3 of 169.7. Why in the world would I write it that way? And you could write it, I could say this was 1/5 of some number 5 times as big. It's kind of silly to say that, isn't it? Well, not necessarily, because what is the volume of a prism with the same dimensions? We get 5.8 on each side and a height of 5. Well, it'll be 5 times 5.8 squared, which is 168.2. Well, that's pretty close to this number here, isn't it? It's 169.7. Well, it turns out that the formula for the area of the pyramid is just the formula for I said area, I'm sorry. Volume of a pyramid. Area of a pyramid really doesn't make sense. You can have surface area of pyramids, but plane area, well, that's doubly dumb because there's no such thing anyway. Volume of the pyramid is what I meant to say. The volume turns out to be exactly 1/3 of the volume of a prism with the same dimensions. That's why I wrote it out this way. Well, this is just a pretty crude approximation. I mean, you can see that these two sets of rectangles don't approximate this pyramid, or in this case the side view is a triangle. They don't approximate it very well, do they? And yet when I take the average, I'm not off by much. And in calculus you can actually make these smaller and smaller, which means they would fit better and better. And you would find that the limit of this blue ones as they went down, and the limit of these yellow, the limit of the volume of these blue prisms, and the would drop down towards this volume. The limit of the yellow prisms would go up, and they would approach the same number as the number of prisms you use to fill this in. As that goes to infinity, the yellow ones, the sum of the yellow ones gets larger, the sum of the blue ones gets smaller, and they approach the same limit, which is in fact the volume of this pyramid. And that turns out to be 1/3 of this. So the volume of a pyramid is 1/3 the volume of the prism with the same measurements. And that is your formula, actually. This is not a proof. It's just it's designed to help you maybe remember it and see the sense of it. You can see why this could turn out to be 1/3, because it actually works. If you break this up into rectangles and start adding them up, you'll find that as you improve the resolution and make your rectangles smaller and smaller, which that's the side view as a rectangle, obviously. The real thing is just a pyramid. You add up all those volumes, you will get 1/3 of what you would have gotten for the whole prism. And you can do exactly the same thing with cones if you want to. You could simply define it to be a 60-degree angle here, which makes this 30, and you could easily demonstrate it for one particular cone. And that's really all this is. It's a simple little demonstration. It's certainly not a proof. For a cone, we get exactly the same thing. We get the base, or let's say the area of the base. For a cylinder, we would have the area of the base times the height. This is a cone. But just like with the pyramid, all we have to do is stick a 1/3 in front of it, and boom, we've got the volume for the cone. It's exactly 1/3 of the volume of a cylinder with the same dimensions, just as the pyramid was exactly 1/3 the volume of a prism with the same dimensions. That's kind of cool, huh? And you could demonstrate exactly what I did before by using pi r squared instead of one side squared and the h's, and you could find r at each level the same way I found the side length at each level, and convince yourself that this actually works. Well, we've had enough fun playing around with prisms and pyramids. Let's work some problems. Here we have one of those oops, somebody goofed problems. What was the mistake here? 1/3, that's the formula, 1/3 times, well, that's a half. It's supposed to be a third. There we go. 1/3 the area of the base times the height. Well, the base pi r squared, that would be pi 9 squared. That makes sense. Times the height, we got, that's not the height. That's what they call the slant height. Remember, we use that a lot for surface area. We don't use it so often in volume calculations. The height is this thing here, which is, well, the square root of the hypotenuse squared minus this leg squared. So if we take 15 squared minus 9 squared, take the square root of that, we get 12. And it's a little bit different from 15, isn't it? So we can take 1/3 pi times 9 squared times 15, or we could multiply this by 12 over 15. That way the 15s would cancel, and we'd have 12 times 9 squared times pi times 1/3, which is what we should have had in the first place. So if we take our incorrect answer and multiply by 12 over 15, we should get the right answer. Doing it this way, we would get 1017.6. Or, if you wanted to do it the other way, you would write out, that's supposed to be a 3, there we go, 1/3 times pi times 9 squared times 12. That would be the correct formula, or the correct numbers to put into the formula. And if you did this, you should still get 1017.6, roughly. Well, looks like our old buddies Inseam and Fleabite just won't give up. They're still trying to get it right. The formula for a pyramid is 1/3 times the area of the base, that's the base here, times the height. Well, the height is 10. Okay, so far that's good. This is 7 squared. They got the little hash marks here to tell you that this is actually a square. So this is 10. This is 49. That makes sense. This is, well, come on. You can't do that. It's 1/3, not 1/2. So, once again, if we wanted to make this 1/3, how could we do it? Well, let's multiply by 2 over 3. Multiply by 2 to get rid of the 1/2, and then divide by 3 to get everything back the way it should have been in the first place. Of course, if we didn't already have an answer for this, doing this wouldn't make much sense, but we have one. All this stuff is 245. Multiply that by 2/3, and we've got the right answer. So here's the correct formula. Gee whiz. 1/3 times 49 times 10, or 1/3 of 490. That's 163.33. Or, given an incorrect answer, if you know what's wrong with it, you can multiply by a correction factor and quickly get to the right answer. Now here's another one of those where they give us some information, and usually the best thing to do is set up the equation you have, which relates the information given, and hopefully what they asked you for will drop out. Let's see how that one works out. 45 cubic feet is the volume. Okay. And that is 1/3 times the area of the base times the height. Oh, they gave us that. That's 9. Okay. Well, if we solve this for a sub b, which is what they asked for, isn't it? Okay, good. Then the area of the base. Oh, we set this up. And let's see, 9 goes into 45 5 times 3. Now you can do this without your calculator. It's 15. And that would be in square feet, of course. So the answer here is D. Whoa. All you had to do was remember your formula for the volume of a pyramid. This was pretty easy. Now this looks easy. It says, what's the approximate volume of the cone? Well, what's our formula? 1/3 the area of the base times the height. Well, area of the base, that would be pi r squared, or in this case, pi times 5 squared. We get 1/3 here, and the height is, 29 degrees. No, we have to remember our trigonometry, don't we? And remember that opposite over adjacent is the tangent. So we can write that the tangent of 29 degrees equals opposite, that's 5, over the height, which is the adjacent leg in this case. Well, we multiply through by h, divide through by a tangent of 29 degrees, and we get that h, if we want to do it this way, equals 5 over the tangent of 29 degrees. We can get an answer for this, or we can just stick it in over here. So this is 1/3 times all of this stuff. And I could have put 3 down here, couldn't I? I could write pi times, well, this is going to turn out to be 5 cubed, isn't it? Pi squared times 5 over 3 times the tangent of 29. That would be exactly the same thing. If you do all that, you get a number something like this, which works out to 236.14 if you don't really round things off. If you actually write it this way and compute it, you get like 236.56. That's because this number here is rounded off. Well, that looks just like this, doesn't it? So the answer is B. And as they said, the approximate volume, you can get, and depending on how you round these numbers off, you get anything from 236.02 to 236.6. They said approximate, but then they added two places here. That seems fairly exact to me. But anyway, this is how you would have done it. All you had to do is remember your formula for the volume of a cone. We've got most of our dimensions. We just had to remember our trigonometry in order to get this height here. And you definitely want to review that. Make sure you've got it down, or just memorize the mnemonic I told you. For the sine, some old hippie, that's sine is opposite over hypotenuse. Cot, another hippie, cosine is adjacent over hypotenuse. Tripping, on acid. Tangent is opposite over adjacent. The first letter of each word represents a trigonometric term. The whole thing is some old hippie caught another hippie tripping on acid. If you remember that, you can always keep straight your trigonometric ratios. Well, back when we found the areas of oddly shaped figures, we usually did it by finding the sum and differences of figures we could actually make sense out of. For instance, if we take what appears to be a cube, well, it definitely is a cube, and cut out a cone, the shape that's left is kind of weird. I don't think we have any real formulas for it. I'm not even sure what you would call it. Just a cube with a big crater in it. However, if we take the volume of the cube, subtract the volume of the cone, we have the volume of this, whatever's left over here, the solid part, we could call it. This doesn't look too hard. I mean, the volume of the cube, that's easy. 5.1 cubed. Okay, we're done. What about this thing? Well, the circle is inscribed inside this cube. So the radius must be half of 5.1. Oops. So for radius, we would get 2.55. What about the height? This is r here, sorry. Well, the height is still just 5.1, right? It looks like the tip goes right down to this bottom base here, and the circle is right here in the top base. So the height is 5.1. So for a cone, we get 1/3 of pi times 2.55 squared times the height, which is 5.1. And if we do all this, 5.1 cubed minus the volume of the cone, that's 132.65 minus 34.7. And depending on whether you use the pi button or and how you round stuff off, you get about 97.93. You might be different in the hundredths column because of round off. But if you got something close to that, you did it right. And again, this is fairly simple. Just remember that when you're looking for the volume of odd shapes like this, you just take the sums or differences of the volumes which you can find. In this case, we could find the cube and we could find the cone. So all we do is take the volume of the cube and subtract out the volume of the cone, and that's what's left over. So all we had to remember was the volume for the cube, volume for a cone, and then we subtract the two to get the volume of this little odd shaped figure here. Well, what we have here is the regular hexagonal pyramid, and I think they want us to find the volume. Yes. Well, it'll be just like what it always is, 1/3, and that's the nice thing about writing it as the area of the base, because it doesn't matter what the base turns out to be. In this case, it's a hexagon, times the height. Well, first thing I would do is find the area of the base. That would be the area of this hexagon here. And then we'll work out the height, because they didn't give us the height. They didn't give us the area of the hexagon either, for that matter, but we can figure that out pretty quick, and then we'll get the height. Now here's a top view of our hexagonal base. Has side equal to 3. We need to know the altitude so we can figure out the area of this triangle. When we got that, we'll just multiply it by 6. We did this before. Well, this will be 60 degrees, right? 360 over 6. That means this part right here is 30 degrees. And this little half, this section right here, this is 3 over 2. Remember, this whole thing is 3. So this part right here, this is just 3 over 2. So tangent of 30 degrees, which we know is 1 over the square root of 3, equals opposite over adjacent. That's 3/2 over A, or 3 over 2A. That's an awful 3. There we go. That's kind of a 3. Or we could write this as, this implies that A equals 3/2 times the square root of 3. So the area of one triangle is going to be 3/2 times the square root of 3, that's the altitude here, times 3, times 1/2, because that's the area for a triangle. Altitude times the side length times 1/2. So if we multiply this all out, what do we get? Well, if we do all this, we get the area of one triangle, this little thing here, is 3.89. We multiply that by 6 and get the area of the base that we're looking for here. And it's going to be 23.4. You see how we did that? Pretty easy. Now I'm going to need some more room because I have to figure out the height here. But they gave us this angle. This is 35 degrees right here. That's ABC. And what are we going to do? Well, this has length 3 because that is the same as this. How do we know it has length 3? Well, this is a hexagon, right? So this is 60 degrees. But these two, being the radii for the hexagon, have the same length. That means these two base angles have the same length. Well, if this is 60, there's 120 degrees left over to divide up between these two evenly, which means 60 and 60. Well, wait a minute. We got a triangle with 3 60-degree angles. We automatically know that's an equilateral triangle. So this hexagon is made up really of 6 equilateral triangles. That means if this side is 3, then this is 3, and this is 3. So we don't have to even do any calculating to figure out that this radius right here is equal to 3. Well, that kind of simplifies things, doesn't it? Now that we know what this is, we can use the tangent, opposite over adjacent, and get this height here. So if I set this up, tangent of 35 degrees is opposite, that's h, over adjacent, and it has length 3. I get that h equals 3 times the tangent of 35 degrees, or about 2.1. That's the h I'm going to use over here. Well, looks like I got everything I need, right? We got the area of the base. Now we've got the height. If we use the formula for the pyramid, hopefully we'll get the right answer here. Let's take a look. Now, if we do all this, I get 16.38. And that is, in fact, the volume for this pyramid. All we had to do was remember how to figure out the volume for a hexagon. Then, remember our trigonometry to get the height, given that this is 35 degrees. If they hadn't told us that, we might have been in trouble. And then, just apply the formula. Actually, quite a bit easier than it looked at first glance. Here's a problem that I think is more interesting if we just work it out generally, because part C is going to ask you for general answers. I think we can probably do this without the numbers. I'm going to say this has height h and side length s. In other words, we're going to do it this way and see what happens. Now, the volume for the pyramid is 1/3 h s. Okay. Now, what happens? This is, let's say, that volume for the pyramid. Okay. Now, let's let's see here, the base stays the same, but the height is double. Well, okay. Then our second pyramid, we'll call that the pyramid prime. That pyramid has height, or pardon me, volume 1/3 times 2h times s, which equals 2 times 1/3 hs, or 2 times the original volume. So what it did was it doubled the volume. Now, suppose we leave the height the same and double the base. Well, what happens when you double the length of a square? You square the area, don't you? So something very similar is going to happen here. I wrote out the volume for the pyramid. I forgot to put the little square up there on top of the s. Pardon me. It's s squared for the area of the base. S squared, s squared. So our next volume for our third pyramid, we'll call that V double prime for the pyramid, is 1/3 h times 2s. That now is our side length squared. Well, wait a minute, what's that going to be? That's 1/3 h, well, 2 squared is 4, times s squared. We pull out the 4, and we're back to our original volume. 4 times, or and I bet that's pretty much what you expected, isn't it? Well, that's about it.